In the last lecture, we discussed Rutherford's model of the atom. You recall that Rutherford did the experiment on alpha scattering, and from that he thought that the atom must consist of a very heavy center, that is nucleus, and the electron must revolve around it just like the planets do around the sun. This model had a very severe shortcoming, very serious shortcoming, and that was this, that the electron that is orbiting the nucleus is accelerated all the time, and according to the laws of electrodynamics, an accelerated electron must radiate energy. So, if the electron radiates energy, then it loses energy and slowly it falls back on the nucleus. That means that this model of the atom is not a stable atom. This shortcoming was removed by Bohr's model. According to Bohr's model, the orbits of the electron around the nucleus are stable or stationary orbits. The electron cannot take every orbit, but it can take only some orbits, some selected orbits, and these orbits are stable. Then we found that if an electron jumps from a higher state to a lower state in the atom, then it radiates energy equal to the difference of the two states, or if the atom can get energy which is equal to the difference of energy in the two states, then it can absorb that energy, that photon of energy. So, the atom can emit energy, the atom can also absorb energy, and at the end we discussed this ionization potential. I showed you the energy states of the atom, and if the electron is pulled out from the ground state to outside the atom, then the energy required is called ionization potential or ionization energy. Now, today we shall go into greater detail of the Bohr model. We have already defined ionization energy or ionization potential, and for the hydrogen atom, for which Z the atomic number is 1, and for the ground state n is equal to 1, the energy of the electron in the ground state is minus 13.6 electron volt. This is the energy that I must give to the atom to take this electron in the ground state out of the atom or to ionize the atom, and therefore, the ionization energy of hydrogen is 13.6 electron volts. For the energy, there is a n square here, which we have not written because of n equal to 1. That means, as we go to higher states, the energy changes by a factor of 1 by n squared. So, the energy in the second orbit n equal to 2 is 1/4 of this, that is, and in the third orbit from the nucleus, the energy would be 1/9 of this. Now, notice that n actually, as n increases, the magnitude of the energy is decreasing. Remember that it will be 1/4 of this for the second orbit, 1/9 of this for the third orbit. So, the magnitude is decreasing. However, since this is a negative sign here, the energies are negative, minus 13.6, minus 13.6 by 4, minus 13.6 by 9, the magnitude is decreasing, but the actual energy is increasing because of this negative sign. So, if an electron falls from the orbit n 2 to a lower orbit n 1, n 2 is greater than n 1, lower orbit n1 and higher orbit n2, then the difference of energy delta E is given by this expression. This minus sign here, remember, and this is 1 by n2 square minus 1 by n1 square, and this difference of energy is what is radiated. The frequency of the photon emitted by the atom will be given by nu, which is equal to delta E by h, where h is Planck's constant, and the wavelength would be given by 1 by lambda, which is delta E by h c, equal to m z square k square E 4 by 4 pi h crossed cube into c, multiplied by 1 by n 1 squared minus 1 by n 2 squared. I have absorbed this minus sign here. This quantity R is the Rydberg constant, and for hydrogen, for which Z is equal to 1, the Rydberg constant has the value R h m k squared E 4 by 4 pi h crossed cubed into c, and if you substitute the values, you get 1.097 into 10 to the power 7 meter raised to power minus 1. So, that is the value of the Rydberg constant for hydrogen. So, we can write 1 by lambda equal to R h into 1 by n 1 squared minus 1 by n 2 squared for hydrogen. If the transition takes place from the excited states to the ground state, the series of lines formed is called Lyman series. I will show you in a moment. This series is in the ultraviolet region, so it is not visible. If transition takes place from higher orbits to the orbit n equal to 2, the resulting series is known as Balmer series, and this is in the visible region. There are other similar series too. So, here I am trying to show you the energy states of the hydrogen atom. This is minus 13.6, this second one is minus 3.4, the third one is minus 1.51, and the fourth one is minus 0.85. You see, although the magnitude is decreasing, the energy is actually increasing. And now, if the electron falls from any higher state to the ground state, then these series of lines, they are called Lyman series. As I said, they are in the ultraviolet region. If the transition takes place to n equal to 2, then this series of lines is called Balmer series, and Balmer series, some of its lines are in the visible region. Here is the Balmer series, and you can see the lines in the visible region. And we have already talked of the absorption of radiation by the atom. So, if there are series which are in the emission, then when the electron falls from any higher orbit to, let us say, n equal to 2, this gives us Balmer series in emission. On the other hand, if the atom absorbs energy from n equal to 2 up to any level, then these will be lines in the absorption spectrum, and therefore, this would be called the absorption spectrum series, Balmer series in the absorption spectrum. So, what is happening here is this, that there is a background of radiation and the atom absorbs the energy which is just the difference of say n equal to 2 and n equal to 5, or n equal to 2 and n equal to 4, or n equal to 2 to n equal to 3, exactly equal to this difference. And whenever the energy is absorbed from the spectrum, this gives a dark line. Here is a dark line, here is a dark line, and there is a series of dark lines. These dark lines form what is known as absorption spectrum, and these lines correspond to Balmer series, and therefore, these are Balmer series in absorption. Now, I try to show you the same thing again. If the atom, if the electrons move from any higher state to the ground state, we have got Lyman series. If the electrons move to the first excited state, that is n equal to 2, we get Balmer series. If they move to n equal to 2, excited state n equal to 2, then we got Paschen series and so on. A word of caution is necessary about the Bohr model. You see, we are saying that there is a nucleus and electrons are moving around the nucleus in orbits like the orbits of planets around the sun. This is only a pictorial representation. It is a good picture, but it is misleading. Why is it misleading? Because if you want to plot the orbit of an electron, you need its position and its velocity at a given instant of time, so that you know where it would be at the next instant of time. But this is not possible, because Heisenberg's principle of uncertainty says that you cannot know both the position and the velocity of the electron at the same instant. The knowledge of these two is prohibited by the uncertainty principle, and therefore, this is not the true picture. What is the true picture? Now, we talk of not orbits, but orbitals. And what are these orbitals? These orbitals are actually the clouds of probability density. You see, this is a fuzzy thing, there is no orbit, the whole thing is like a cloud, and this is the cloud of probabilities, and wherever the density of probability is high, there is likelihood of electron to be found at that location. So, since there is this caution about the Bohr atom is a good model as far as the explanation of the spectrum is concerned, and spectrum of only hydrogen or hydrogen like atoms, but it is not the true picture, it is just a pictorial representation. So, while the progress was being made in the atomic physics, we had the Thomson's model, then Rutherford model, Bohr model and so on. So, while the progress was being made in atomic physics, important developments were taking place in other fields of physics also, and the two of these developments are very important for us. And one I have discussed several times, and that is the difficulty in explaining the spectrum of a black body. Black body is any body can radiate, and when heated or when given a higher temperature, it can radiate. Even when it is not given any higher temperature, it can radiate, but the intensity would be low, and this is known as black body radiation. And the black body radiation could not be explained towards the end of the 19th century. The difficulty was that the existing this law or the Rayleigh-Jeans spectrum, this could not explain, because this is the black body radiation, Rayleigh-Jeans spectrum is like this, and therefore, this classical Rayleigh-Jeans spectrum could not explain this, because we assumed that energy is continuous. Planck at the end of the 19th century said no, energy of a radiator is not continuous, it exists in discrete quanta. And if you make this assumption that the energy exists in discrete quanta, then you can explain the black body radiation very well, and that is what Planck did. This we have discussed several times, and these discrete bundles or quanta each has energy h nu, and instead of a continuum energy, you cannot have any energy, you have energy only in the form h nu, and h is Planck's constant, nu is the frequency. So, if you assume that a radiator has energy in these bundles of energy h nu, then you can explain the black body radiation. If you assume it is continuous, then you cannot explain the black body radiation. And you remember that this idea of quantum of radiation of energy h nu was used by Einstein to explain photoelectric effect. But this quantum h nu, although the energy is discrete, there is in this discrete energy we have frequency, which is a continuous function. Therefore, there is now you see some kind of a connection between the particle picture and the radiation picture. Nu is the characteristic of a wave and discrete energy is the characteristic of a particle. So, we have a sort of relationship between particle and wave. This is known as duality, and we shall now try to explain what is this duality. The other important development concerns the explanation of atomic spectra by Rydberg, which we have partly discussed. 1 by lambda is given by R h into 1 by n 1 squared minus 1 by n 2 squared. So, Rydberg derived this formula, and Bohr model was initially developed to explain this, and this it did with great efficiency, or it did admirably. So, we have so far been introducing the nature of matter, and having done that, we are now in a position to show that matter actually has dual nature. I have already hinted at the dual nature in the formula E equal to h nu. First, we discuss phenomenon alluding to particle nature of electromagnetic waves. We shall show that electromagnetic waves behave as particles. The most well known, the emission of electrons from metal surface when they are given the necessary energy by some means. The electrons that are emitted are free electrons in the metal. Now, what are these free electrons? Again, we have discussed this several times. You see, the orbit round the nuclei in various, the electron orbits round the nuclei in various orbits, and as the number density of atoms is very large in a metal, these orbits they get crushed against one another, and some of the electrons do not belong to any of these orbits. It could be at some time belong to this, or sometime could belong to this. These electrons which are delocalized, that means they do not belong to any particular orbit, they are called free electrons. Why? Because these electrons, say one here, one here, one here, these electrons can move around almost freely within the atoms, and these electrons therefore are called free electrons, and these are free. These free electrons are the ones which can be emitted by the surface of a metal when energy is given to it. You see, these are free electrons and they are moving in random directions. They are within the surface, they cannot come out by themselves. We have to give them energy so that they come out, and the minimum energy required that must be given to them so that they can come out is known as the work function of the metal. There is a minimum energy that must be provided to these electrons to come out to the surface without any kinetic energy, and this energy that is given to the electron to come out to the surface is called the work function of the metal. And we have listed here work function of a few metals. For aluminum, the work function is 4.08 electron volts. For calcium, for cesium, gold, iron, silver, uranium, all these metals, and the work functions are given here. That means, if we have say gold piece, and if we want to remove the electrons from the gold to the surface of this piece without any kinetic energy, then we must give to each electron energy equal to 5.1 eV. This is therefore the work function of gold. The energy required for the electrons in this metal gold to come from within a piece of gold to the surface of that piece. This energy is 5.1 electron volts, and this is known as the work function of gold, and it is denoted by the Greek letter phi. Now, the work function of a metal depends on its structure, its purity, and on the condition of the surface. Obviously, metals selected for devices using electron emission must have low work function, so that the energy given is not very high. How can we provide energy to the electrons? There are various ways. One is we heat the piece of metal. When we heat it to a high temperature, then enough energy can be provided for the electron to come out. We can exert the electrostatic field, exert pressure or exert force by electrostatic field. Here is a metal surface, we apply a strong electrostatic field, and this electrostatic field works on the electrons, attracts the electrons, and if the field is sufficiently strong, if it provides sufficient energy, then electrons can come out. This, or we can throw or bombard the surface of the metal with electromagnetic waves, high energy electromagnetic waves, or we can bombard the metal with particles like electrons. So, there are various ways in which the energy can be provided to the electrons to make them come out of the metal piece. When, as I said, you heat the piece of metal, then electrons, if heating is sufficient, it provides sufficient energy to electrons, then electrons can come out. And this kind of emission of electrons from a metal surface, when it is heated, is known as thermionic emission. Thermionic, therm for heat, thermionic emission. It is interesting that thermionic emission was discovered by Edison in the 19th century, while he was trying to improve the design of the electric light bulb. Although he did not find this discovery useful, it was picked by other scientists, and this led to the development of vacuum tubes. It must be remembered that vacuum tubes ushered in the science of electronics, which has played an extremely important role in the development of devices which have touched almost every aspect of our lives. So, for the next lecture, we will continue with the emission of electrons. We have done thermionic emission. We will next do emission by electrostatic field, known as field emission, and we shall see how field effect has been used to make field effect displays for high definition picture tubes. These days you have the LED televisions in your homes, and these LED televisions, they are high definition televisions, and we use what are known as field effect displays, which give you the definition, high definition picture that you see. We shall see how it works. Then we shall come to photoelectric effect. Photoelectric effect is when you throw electromagnetic radiation on a piece of metal and make electrons come out of the metal. This is known as photoelectric effect. So, we shall study photoelectric effect, and we shall study the effect of intensity of light, frequency of light, and other things on the photoelectric effect. And at the end, we shall propose, as Einstein did, quantum hypothesis for the explanation of photoelectric effect.